two systems come into thermal contact. Okay? So we have two systems, A and B, and then they're going to come into thermal contact, meaning that they can exchange kinetic energy through collisions until no more net heat flow. Okay? Heat can still flow back and forth, but there's no net change. They've come to equilibrium. They've reached the same temperature. Okay? Temperature is a relative measure of average kinetic energy. Okay? So in these illustrations, we're assuming each energy level is associated only with kinetics. Okay? All of these molecules are, say, just a point for an ideal gas molecule. Okay? They don't have potential energy right now. So how would I get the average kinetic energy of, say, system A right here? It's the total kinetic energy, keeping in mind that I'm telling you these energies are only kinetic. It's 10, right? So we could sum it up. We could go, there's, n of 1 and 0, 1 times 0, 1 times 1, plus 1 times 2, plus 1 times 3, plus 1 times 4. This is also given to us. So the energy of the system is 10. If I divide it by the number of molecules, I5, the average kinetic energy of this system would be 2. 10 divided by 5. And the average kinetic energy of this system is 1 divided by 5, or 1/4. This system has a higher temp. It has a higher average kinetic energy. This system here has a lower temp, which they've chosen obviously to illustrate with blue as cold and red as hot. So straightforward. Okay, temperature 2 is colder, and when they come together, eventually heat will flow from the hot system to the cold through kinetic energy transfer until they reach a temperature that is going to be in between. And in this case, that temperature is the same for all of these, because total kinetic energy is conserved. Yep.
So is the total energy equal to the kinetic energy of small time?
Yes, in this particular oversimplified case, I've said we're only considering kinetic energy, and all of these are a single point. They don't have anything else going on. They're just treated like a monatomic ideal gas. I have a review slide that reminds you, FYI, real molecules have potential energy too. Okay. So yes, this is we're operating under the assumption kinetic energy is all that's here. And so you can run through and check this. These all have the same total energy, right? It's going to be 12 because these are, the wording in your homework will be they're isolated from the environment, meaning they can only exchange energy with each other, and the total energy will be conserved and no energy will be lost anywhere else. Okay, so they'll all have 12. And if you divide 12 by what is now 10 total molecules, you'll get 1.2. So you'll have this temp that's in between. These are 3 microstates of the same macrostate. They all have the same total energy and the same total number of molecules. U is the same and N is the same. Even if the energy is distributed differently, you have 2 or more microstates of the same macrostate. If these things are satisfied, they're the same across the board. How do you decide which of these microstates is most likely at equilibrium? And your choices are this one here, or this one here, or this one here. Left, middle, and right. Yes?
It's the one that minimizes.
So this is a great point. Minimizing energy is one goal in sort of overall systems. They want to minimize energy. Now energy is the same in all of these though. It's 12, and it just is 12. Okay? So they all still sum to the same total thing. So then what's the other half that we can consider? Maximizing entropy. Okay? So you could run yourself through and do multiplicity of each of these systems, and see which one is highest and know that that's the one that would give highest entropy. You don't need to do that. You can just look at them. Yep.
So what if both energy and entropy differed?
Gibbs. Welcome, Gibbs. You're beautiful. 10-ish slides ahead of the game. Yep. Those are two things that are in competition, minimizing energy and maximizing entropy. Okay? So given what we have here, they're all the same energy, we'll think only about trying to maximize entropy. Okay? I won't give you the answer because it's essentially the same thing as one thing on the homework. So think about how to do that on your own without doing a calculation. And that doesn't mean do your calculation on a paper on the side and then write that on your homework without showing it to me. Yeah.
Or since it's supposed to be the same, is it possible that the energy levels are the same but they have different number of molecules?
No.
So the,
You need to have, to be two microstates of the same macrostate, you have to have the same ends and the same total U. How you divide your molecules among energy levels to get the same total energy is fine, right? Because you can see here, 4 molecules are in the 3rd level, but 6 are in the 0, looks different than this, looks different than this, but if you sum them up, they're all gonna have energy 12, and they all have 10 molecules.